Yeah, in this lesson, we are going to look at how to differentiate composite functions. Or in some books, you hear chain rule, function of a function. So we want to consider differentiation of composite functions. Composite functions. So if you are differentiating a composite function, that is a function of another function. The process is what we call the chain rule. What we are saying is that if y depends on u, and u also depends on x, y is a function of u is a function of x, and you want to differentiate y with respect to x. That is, you want to find dy dx. You want to differentiate y with respect to x. You can't jump over u because u depends on x and y is depending on u. So what we do is that you have to find dy du. You are going to differentiate dy du. Then from du, you move to du dx also. So this side will be du dx. And you take the product. So when you multiply dy du by du dx, then you get dy dx. So it says that the dy dx will now be equal to dy du times du dx. So you have to differentiate with respect to u first, then you find du dx, then you take the product, then you get dy dx. Note, when you check very well, it appears du is cancelling du. And if du cancels du, then the result is dy dx. We go back. So that is how we do composite function differentiation. You can't jump. Y depends on x. Y depends on u depends on x. So to find a derivative, you have to find differential dy du, then du dx, then you take the product. Good. Let's take an example. If y is now equal to, or let's clean the board and have a wider view on the board. If y equal to 2x plus 3 exponent 4, we have to find dy dx. To differentiate such a function, this function is a composite function, because the whole function is to the power 4, and there is a linear function inside the original function. So it tells you that to get dy dx, you have to consider the 4 too. You can't just differentiate as you have been doing, and you can expand using binomial expansion. That work will be very tedious. So you apply the chain rule of differentiation of composite function. So the chain rule says that if you let u to be equal to 2x plus 3, then the whole function here becomes u equal to y equal to u exponent 4. So whenever you see 2x plus 3, you are putting u. So if you put u here, it will be u power 4. Then you want to find dy dx. Y depends on u. Du depends on x. So you have to find u dx. Du dx, and the result is 2. Then we find dy du, and the result is 4u exponent 3. And to get dy dx is now going to be dy du times du dx. That is the product rule. And in that case, dy du is defined as 4u cubed times du dx, which is also 2. And the result is now 8 u exponent 3. But our u is defined earlier as 2x plus 3. So we substitute the value of u into the final results, and the answer is 8 of 2x plus 3 exponent 3, and that becomes the final answer to the problem. You can also differentiate this one differently. That one is shorter than this process by making these substitutions. So let's see one other way you can use to solve the same problem. It's the same chain rule. Instead of trying to come out with a u and getting your y in u, you can differentiate the function as you see. Dy dx is now differentiate, and it will be 4 of 2x plus 3, then 4 exponent 4 minus 1, that is the normal differentiation, times ddx of the inside function, which is 2x plus 3. And that is a chain rule being quoted in the simplest form. So we can now write 4 of 2x plus 3 exponent 3. Then differentiating this side will give us 2. And when you take the product, it is now 8 of 2x plus 3 exponent 3, and that is the answer. Very simple. So as we move forward, it is not all the time that you have to make u be equal to. You can go by this process and you get the answer. Let's pick another example. We want to differentiate y equal to 3x minus 1 exponent 9. To differentiate such a function, you find dy dx. Then you differentiate the total function, then it is 9, 3x minus 1, subtract 1 is 8, times d dx of the inside function, which is 3x minus 1. So differentiating that function, it will give us 9 of 3x minus 1 over 8. Differentiating the result is 3. And 3 will multiply 9, and the result is 27. 3x minus 1 exponent 8 gives you the final answer. So that is what you should be considering. Anytime you have such a function, you can differentiate using the chain rule because it's a composite function and chain rule is applied. Let's pick another example and see how it will be done. We have to determine the differential coefficient of such a function. If y equal to root of, if you have a function which is a radical function, 3x squared plus 4x minus 1, we have to find the dy dx. We have to find dy dx of such a function. And we can rewrite this function solution. Y is now equal to 3x squared plus 4x minus 1 Good. Exponent half. So when it is written this way, it becomes a function of a function. So we differentiate dy dx. Half for multiply, we have half 3x squared plus 4x minus 1. Subtract 1, negative half. That is when we subtract 1 from half, the answer will be negative half. Then we multiply by d dx of the inside function, which is 3x squared plus 4x minus 1. The rest is algebra. We try to simplify and see what we will get. So this side is now half 3x squared plus 4x minus 1 exponent negative half. Differentiating that term, it will give us 6x plus 4. Good. So when you have such a solution, you can simplify further. And we now have half times 1 over, the negative index can change to positive. So it becomes 1 over 3x squared plus 4x minus 1 all power half. Then it will also multiply by 6x plus 4. Good. Let us still, there is a common factor here, which is 2, because there is half sitting here. So let's factorize and see the result. So we will have 2 out, 3x plus 2 all over half, which will also be 2 here, root of 3x squared plus 4x minus 1. Then into square root sign. So the 2's will cancel and the final answer will now be 3x plus 2 divided by root of 3x squared plus 4x minus 1 becomes the final answer. Thank you. Good. We want to consider differentiation by the quotient rule. Or differentiating rational functions, quotient rules are applied. So, quotient rule. The quotient rule says that if you have y equal to u out of b, where both u and v are functions of x, that is, the functions are rational functions. It says that to find the derivative, if this one is it, then dy dx will now be equal to, we maintain the denominator first, v, then you find du dx minus, you maintain u, then you find dv dx, then you divide the result by v squared. Please, the proofs are there, but we just want to know what the concept is now. Later we will look at the proofs. The proofs are there. So to find derivative of a rational function, maintain the denominator first, because the terms are subtraction. It's not like the product rule whereby you have addition. This one they has been subtracted. So subtraction is not commutative. So if you do the last term before the first term, you score 0. So you always maintain the denominator first, then you differentiate the numerator, followed by you maintain the numerator, then you differentiate the denominator, then you find you square the denominator. That is the quotient rule. For example, if I have a function like if y equal to x plus 1 divided by x minus 1, and you have to find dy dx. What it means is that you are going to apply the quotient rule to differentiate such a function. So our dy dx will now be equal to, we maintain the denominator first, and it is x minus 1. Then we differentiate the numerator. That one becomes d dx of x plus 1 minus. Then the rule says you have to now maintain the numerator, which is x plus 1. Then you find d dx. That is, you differentiate the denominator, which is x minus 1. Then all divided by the denominator square, which is x minus 1 all square. Good. We can finish it here. So our dy dx is now equal to, we try to maintain x minus 1, then you differentiate x plus 1, and the result is 1, minus, you maintain x minus 1, then you, x plus 1, sorry, then you differentiate this side, and that side too will be 1, all over the denominator, which is x minus 1 all square. Let us so we can now find x, expand, x minus 1. Then expand with negative 1 minus x. Then we also have negative 1 also, all over x minus 1 all square. And when you simplify, the x's will disappear. It will be x minus x, and it will be 0. But negative 1 minus negative 1 is negative 2 all over x minus 1 all square. Good. So an example on quotient rule is what I have demonstrated. Let's pick one more example and see how it will be done. So if you have y equal to a function like x squared over x cubed plus 1, how do you differentiate using the quotient rule? Some will let solution. You want to find your ideas. So let u be equal to x squared. Then we have the v to be equal to x cubed plus 1. Then we find du dx. To get du dx, we are differentiating u with respect to x, and that one will be 2x. Then we also find dv dx. That is differentiate v with respect to x, and it will be 3x squared. Now, the question is, what will be dy dx? By the quotient rule, it is strictly v du dx minus u dv dx all over v squared. So if it is okay, we make these substitutions into our formula. And what is our v? Our v is x cubed plus 1 times du dx, which is 2x minus, you maintain the u. And what is our u? X squared times dv dx. And dv dx is now 3x squared all over v squared. And our v is now x cubed plus 1 all squared. Good. We can now continue the solution at this level. We do expansion and see what we will get at the end. So let's expand. X times s cubed. 2x times s cubed will be 2x exponent 4. Then plus 2x. That is when 2x expands this bracket. Then we also have minus this times that, and it will be 3x exponent 4 all over x cubed plus 1 all squared. Better still, these are of the same powers, so we can do subtraction. 2x power 4 minus 3x power 4. That one will give us negative x power 4. And we now have 2x minus x power 4 all over x cubed plus 1 all power 2. All power 2. Thank you.